Okay, we're moving into chapter 25, the chapter on mathematical statistics. This is a continuation of chapter 24, which primarily covered probability, although we did at the end of chapter 24 begin to get into subjects like distribution functions, the binomial distribution function, etc. This chapter we're going to talk much more about how to use statistics and statistical testing on data sets and data analytics. So the first concept that we need to get across is that of point estimation of parameters. So basically what happens here is you're going to make a point estimation of parameters. Parameters are quantities that appear in distributions like p in the binomial distribution, the mean, the variance, and the standard deviation in the normal distribution. And so a point estimate of a parameter is a number that's computed for a given sample, and it serves as an approximation of the unknown exact value of the parameter of the population. So we talked before about how if we wanted to make some statement about the average height of women in Nigeria, that we would not want to measure the height of every woman in Nigeria. We would want to measure the height of a sample population and then generalize that to the population. So it's important to keep in mind when discussing statistical representations that you are talking about a given sample and not the entire population. However, this is extremely important practically because in very few cases can we actually sample the entire population. So some examples of point estimates might be moments or the maximum likelihood, and as we discussed before, the variance, the standard deviation, the mean. So let's discuss for a moment the concept of confidence intervals. So a confidence interval gives you the probability that a parameter will occur within a certain interval of values. So let's say I want to know whether or not your test grade will occur in the interval between 90 and 100. So that's a confidence interval. So I can say, for example, I'm 95% confident based on statistical indicators that your grade on the next exam will fall between 90 and 100. And we use this terminology CONF to denote a confidence level. So confidence intervals are more valuable than point estimates. In fact, you could take the midpoint as an approximation of the parameter, and you can think of it as almost like an error bound. So if you assume you have n observations in some random variable x, basically you think about x1 to xn as a single observation of n random variables, and that all of those random variables will have the same distribution. In that case, you have some interval from theta 1 to theta 2 where you have a theta 1 value of x1 to xn and a theta 2 value of x1 to xn. And those are observed values of two random variables. And the random variables would be the actual variable itself. So height, weight, age, etc. So now, basically you can say that the probability that your observed variable falls between theta 1 and theta 2 is in fact gamma. So I think this will become much more clear when we look at some concrete examples. And going through the concrete examples, we're going to use the tables at the end of your textbook. So first of all, we're going to let x1 to xn be independent normal random variables, each of which has a mean of mu and a variance of sigma squared. In that case, then the following holds. If you sum up all of your independent random variables, you will also have a mean n times mu and a variance n times sigma squared. And so the random variable x bar is normal with mean mu and variance of sigma squared over n. And so x bar is basically just the mean of your x1 to xn. Z is going to be a normal with mean 0 and variance 1, because what we're going to do is we're going to take this x. Okay, now remember, x is our average value. We're going to take x and we're going to subtract mu, which is the mean, and we're going to divide by sigma over the square root of n. Notice that's the square root of this parameter here. And so here in this distribution we have a mean mu. Subtracting the mean puts the mean at 0. We have a variance, sigma squared over n. If we divide by the square root of variance, then that puts the variance at 1 when we actually find the variance for this random variable z. So the reason we'd want to do that is this normalizes our random variable and allows us to use various tables. So now what do we mean by a confidence interval? So a confidence interval for the mean of the normal distribution with a known variance. Okay, so in this case, we know the variance. And so now what you have to decide is how confident do you want to be that you're going to get a correct estimate of the mean. So do I want to be 95% confident, 99% confident, or so on? So we have this little table that tells you for an actual variable or an actual choice of confidence level, and in this particular table we're going from 90% to 99.9%. We have this parameter c given in the second row. So now what you do is, given your sample x bar of x1 to xn, you compute this variable k. So k is c, which you look up on the table, times sigma, your standard deviation, divided by n, square root of n, your number of samples. And so when you do that, you basically find then that you can define a confidence interval, x bar minus k to x bar plus k. Okay, now what does this mean in actual words? This means, let's say I want to know, so let's say I have a set of data points, x1 to xn. And I want to be able to say with 95% confidence that that set of data points represents the general population. Okay. So what I do then is I take and I look up, if I have a known variance, I look up this variable k. And then I take the mean and I subtract k and I add k. What that's going to tell me is, that's going to tell me the range over which I can have 95% confidence. So let's say my average turns out to be, or let's say my mean, my value of mu turns out, or my x bar turns out to be 2.4. When I run through these calculations, I might get for the left-hand side of the limit 2.2 and the right-hand side of the limit 2.6. So now what I can say is I can be 95% confident that my mean lies between 2.2 and 2.6 of the general population. So in other words, the whole thing you're trying to do here is you're trying to say, I've got my sample. I want to say with 95% confidence that my sample represents my general population. And so the way I do that is I determine this confidence interval. Now, if I wanted to say with 99% that my sample represented my general population, then I would take 0.99, determine C, and notice that K, as C gets bigger, K gets bigger. So what does that mean? With 99% confidence, my interval, my confidence interval gets bigger. So I may be able to say with 99% confidence that my mean falls between 2 and 2.8. With 95% confidence, I can say it falls between 2.4 and 2.6. With 90% confidence, I might be able to say it falls between 2.4 and 2.44. So you get the picture. It's kind of a trade-off. You can have a pretty high confidence level that your sample represents your data as long as you're able to live with a range of the mean. Or you can have a lower confidence level that your sample mean would represent your population mean, but you're going to have a bigger range for that confidence interval. So confidence intervals are important, particularly in the social sciences when people often have samples that represent a very small percentage of the population. Now here are those tables in the back of your textbook. The first one gives the normal distribution for a given value of z. You can determine theta of z. In this other table, you can determine your confidence interval given a percent. You can determine your range from the original point to the final point. How to use these tables will be brought out a little better in some of the following examples, but they're here for your reference. Here encircled in this little square is kind of the common range from extremely high confidence from 99.1 to 99.9%. Okay, well, you can prove this equation. I have done some math here to show you how that equation is derived. If you have some variable z and you want to find the probability that that variable lies between minus c and c, remember z is our shifted scaled x. So if you substitute for z in terms of x and then do the algebra, what you find is that your mean minus x is related to your lower bound and upper bound of your range by the standard deviation and the square root of the number of samples. And then you can replace that with k just based on the definition. You can then move x bar to either side, and what you find out is that this mu lies between x bar minus k and x bar plus k, where x bar is your sample mean, mu is your population mean. And then that gives you some value gamma. So here's an example. Determine a 95% confidence interval for a mean of a normal distribution with sigma squared equal 9, using a sample n of 100 values with a mean x bar of 5. So if x bar is 5 and we have 100 values and our variance is known, then basically we have to know that our confidence interval that we desire, our confidence percent that we desire, is 0.95%. So what we don't know then is what are those ranges. So let's go back and look at that little table. That's not this one, but the small one. Let's look at this one. So we're going to come here to 0.95 and we're going to see that our C is 1.960. From there, based on our given variance and our given n, we're going to calculate k. So using those equations, basically we calculate k to be c times the square root of the variance, which will be 3, times the standard deviation, which will be 3, times the square root of the number of values, which will be 10, and from there we get 0.588. So x bar, which was given as 5, x bar minus k is 4.412, x bar plus k is 5.588, and so now our confidence interval is that mu is going to lie between 4.412 and 5.588. So what does this mean? This means that we can say with 95% confidence that our population mean is going to lie between 4.412 and 5.588. Okay, let's look at the problem in a slightly different way. Suppose that we want our confidence length to be 0.04, and we want to know how many samples we have to have for us to be able to say that we have 95% confidence with a confidence interval length of 0.04. Now 0.04 is just 2 times, 0.04 is just 2 times k. And k, remember, is c sigma over the square root of n. And so the unknown here is how large must n be. Now, this is why it is really useful to have everything normalized, because what does a confidence interval length of 0.4 mean? It means nothing until you're normalized. So you can't really think about distributions and use these tables until you normalize everything. So, so you can calculate your number of samples that would be required. That, if you do the numbers, will be 870. Now, this is an interesting figure. It basically shows that for a confidence percentage of 99%, the confidence length is substantially longer. So to go from, or the sample size required is substantially longer. So to go from, if you had a L over sigma of 0.3, to go from a 95% confidence to a 99% confidence requires going from about 170 samples to almost 300 samples. So the greater the confidence you have in your numbers, the bigger your sample size needs to be. Confidence integral if you have an unknown sigma. So a lot of times sigma is unknown, and if that's the case, then the table doesn't help you because sigma squared is unknown. In that case, you